So I'm going to cover 1.1 and 1.2 in this video in case you missed class or want to come back and review later. Alright, so the goal is to talk about individuals and variables in a data set, what kind of variables we have. We're going to talk about different ways to display categorical variables with bar charts and things like that, and also with a little bit with quantitative variables as well. And we'll talk about marginal and conditional distributions. So I'll skip over the announcements here and go straight to it. So there's two types of variables basically that we're going to talk about in this class: categorical variables, which put things into groups or categories, and quantitative variables, which have a numerical value. And there are times where we'll have a categorical variable that is a number, for example, a zip code. But a better way to describe it is that it takes a numerical value for which it makes sense to take an average. So we wouldn't take a group of people and average their zip codes because that doesn't tell us anything. All right, so here's an example of a data set. So we have a partial roster of the Trailblazers. So we can say who are the individuals in this data set. So each individual are the players. So for example, Carmelo Anthony is an individual in this data set, and this individual, Carmelo, is measured on several different variables. Which variables in this list are categorical and which ones are quantitative? So some of these are obvious. Weight is something that's quantitative, right? We see it has a number value. It makes sense to ask a question like, what's the average weight on the team? Position would be categorical, right? Players are put into one of 5 positions, right? And they have these categories such as power forward. Nationality, so American, that's a category as well. Years of experience, that's what that 16 means. He's played 16 years in the NBA. That's quantitative, right? We could say, what's the average number of years? You'll see some R's in here. It's basically a 0, means they're a rookie. Cool, college would be categorical. Birth date's a little weird. This would probably be categorical, although we could easily transform this into age, which would be then a quantitative variable. Another strange one is jersey number. So Carmelo wears the number 00, which is a number but doesn't really have a quantitative value. It wouldn't make sense to find the average jersey number of a basketball player or a basketball team. So although this is a number, that would be a categorical variable, or maybe just an ID number. That one's a little strange. All right, so there's a couple simple ways to lay out some data. So for example, we can have a simple data table. That's what we had before, where we just have individuals get their own row, and then we have a measurement of certain variables across that. So for example, we could have the data of the people in the class, my first period class, so we could have a couple of names and what grade level they're in. So that's one way to represent this. Let me get my face out of the way here. We can also do a frequency table. So if we're really concerned about a certain variable, like what class or what grade level everyone's in, we could summarize the data with a frequency table. So I have 10 seniors in that class and 6 juniors. We can also do a relative frequency table. So this is a word we're going to use a lot in this class. Relative frequency means a percentage. So 10 out of 16 would be 63%. Relative frequency is really, really useful when we want to compare distributions of different sizes. So if I wanted to compare the amount of juniors I have in this class compared to the amount of juniors I have in my algebra class, which has 35 students, comparing raw numbers wouldn't be a really fair way to do it. It makes more sense to compare percentages. Cool, a couple ways to visualize our categorical data. Pie charts and bar charts are good for this. Pie charts are really pretty, but they're not super practical. They're not something you can easily make by hand without getting a protractor and doing some math. So we pretty much will not use pie charts in this class, but you should know how to read one and when it's useful. Pie charts are good at representing parts of a whole, but they're kind of hard to interpret. It's hard to know. I'm looking at this slice and I don't know, it's like 40%, but it's hard to get a good measurement. We could add labels or something, but overall bar charts are just more useful. So some things to remember when you're doing a chart: make sure to always label your axes. So you can see down here, I said this is class level, this is relative frequency. Make sure to label your scale. So I've shown that each one of these bars is 10%, and you'll want a title as well. It's an easy way to lose points on an AP test by not labeling your axes. All right, so let's take a look at some wrong things to do when you're making a graph. For example, here is a graph of the ratings for Kik, which is an app. And you can see that there was a decline in the user ratings at some point in this summer or whatever. But this graph's a little misleading. Can you see why? If we look at the y-axis, it only goes from 4.05 to 4.35. I'm guessing this is a 1 out of 5 stars type rating scale. So although this drop looks pretty dramatic, it has only dropped from 4.3 to 4.1. A better way to represent this would to show the full scale from 0 to 5. So a common way that graphs can be misleading is when the y-axis doesn't start at 0. The reverse of that is that sometimes starting at 0 doesn't make sense. It's a good rule of thumb to always start your y-axis at 0, but in this case, if we zoom out too much, we lose all meaning in our data. For example, here is some data of the average global temperature for every year, which is around 67 degrees or something like that. And it doesn't change much. So you might see a graph like this that's zoomed out so much that you lose all meaning to try to back up the argument that global warming isn't happening. However, it doesn't make sense to include 0 degrees as an average global yearly temperature because it's not possible. If the global temperature were 0 degrees, the Earth wouldn't exist. Or same thing with 120 degrees. So sometimes we can zoom out too much. We can provide too much scale so that we lose the trend here. We can't see that this has increased a degree or two, which is not good. All right. Another common mistake made when graphing things out, you'll see this in a lot of ads, is a violation of something called the area principle. So this is a bar chart, or at least it's trying to be a bar chart, but you can see each bar doesn't have the same width, which causes us to perceive this as much, much bigger than that. So you can see this, the DirecTV, who made this ad, has 95 HD channels, but this Dish Network only has 81. So it's only 14 more. It's only about a 10% increase or so. But you can see this bar is 2 or 3 times bigger than the Dish Network bar. So you want to make sure when you're making a bar chart, all of your bars are the same width. You're only comparing different heights, okay? Not comparing multiple dimensions. Okay,